Remember the time when the warm glow of the morning failed to fill you with joy, but instead it filled you with concerns regarding the depletion of the environmental celeb, the ozone. The brave little band of defenders, the ozone molecules, are being tickled and irritated by the merciless invaders, the CFCs, or the chlorofluorocarbons, since the 1930s. But guess what? Our Aussie ozone is rising to become stronger than before to defend us from the cauldron of hot gases, the sun. Since the olden days of space exploration, space scientists have taken the threat of contaminating the celestial bodies very seriously. Since the 1920s, ozone has been measured by ground-based instruments. Scientists place these devices at locations around the globe to measure the amount of ultraviolet radiation getting through the atmosphere at each site. From these measurements, they calculate the concentration of ozone in the atmosphere above that location. These data, although useful in learning about ozone, are not able to provide an adequate picture of the global ozone concentrations. The amount and distribution of ozone molecules in the stratosphere varies greatly over the globe. Ozone molecules are transported around the stratosphere, much as water clouds are transported in the troposphere. Therefore, scientists observing the ozone fluctuations over just one spot could not know whether a change in local ozone levels meant an alteration in global ozone levels or simply a fluctuation in the concentration over that particular spot. So how was this tackled? Our unmanned friend satellites have given scientists the ability to overcome this problem. The Nimbus satellites were a series of 7 Earth observation satellites launched by NASA over a 14-year time period, one of which did not achieve the orbit. In total, the satellites provided Earth observations for 30 years and collectively carried a total of 33 instruments, including ozone mappers, the coastal zone color scanner instrument, and microwave and infrared radiometers. Total Ozone Mapping Spectrometer (TOMS) measured the solar irradiance and the radiance backscattered by Earth's atmosphere in 6 selected wavelength bands in the ultraviolet. TOMS scanned in 3-degree steps to 51 degrees on each side of the subsatellite point, in a direction perpendicular to the orbital plane. Consecutive cross scans overlapped, creating a contiguous mapping of the ozone layer. It was the first to measure ozone columns and profiles from space, which led to the very first confirmation of the ozone hole and the documentation of the recurrence of the hole every year during Southern Hemisphere springtime. These confirmations backed researchers of scientists and aided policymakers in determining the solutions to the ozone depletion problem. Faced with the strong possibility that CFCs could cause serious ozone depletion, policymakers from around the world signed the Montreal Protocol Treaty in 1987, limiting CFC production and usage. The United States Satellite Measurement Program for ozone, run jointly by NASA and National Oceanic and Atmospheric Administration, or the NOAA, has measured ozone distribution by seasonal latitude and longitude and has observed long-term changes over more than 20 years using a variety of satellite instruments. Today, instruments on board the Aura satellite measure traces of gases in the atmosphere, detecting their unique spectral signatures. Microwave Limb Sounder, or the MLS, observes the faint microwave emissions from rotating and vibrating molecules. High-resolution dynamics limb sounder, or the HIRDLS, and the tropospheric emission spectrometer, or the TES, observe the infrared thermal emissions, also due to molecular vibrations and rotations. Ozone Monitoring Instrument, or the OMI, detects the molecular absorption of backscattered sunlight and the visible and ultraviolet wavelengths. NASA monitors ozone from space using microwave limb sounder and ozone monitoring instruments. The MLS also measures trace gases containing chlorine. Along with NASA's R satellite, the NASA NOAA Suomi National Polar Orbiting Partnership satellite and the NOAA's Joint Polar Satellite System, together they monitor ozone from outer space. At the South Pole, NOAA staffs launch weather balloons carrying ozone measuring sounder, which directly sample ozone levels vertically through the atmosphere. Most use at least some levels of the stratosphere, the region above the upper atmosphere where the largest amount of ozone is normally found, are found to be completely devoid of ozone. Stratospheric ozone is being depleted worldwide, partly due to human activities. Scientists now know that the large polar ozone losses are a direct result of the effects of human-produced chemicals. However, scientists still do not know how much of the mid-latitude loss is the result of human activity, and how much is the result of fluctuations in natural cycles. Much remains to be learned about the processes that affect ozone. To create accurate models, scientists are studying simultaneously all of the factors affecting ozone creation and destruction. Moreover, they must study these factors from space continuously over many years and over the entire globe. NASA's Earth Observing System, or the EOS, will allow scientists to study ozone in just this way. The EOS series of satellites will carry a sophisticated group of instruments that will measure the interactions within the atmosphere that affect ozone. Building on the many years of data gathered by previous NASA and NOAA missions, these measurements will increase dramatically our knowledge of chemistry and dynamics of the upper atmosphere and our understanding of human activities that are affecting Earth's protective ozone layer.